Well, it's lecture 18. Okay, so we have many things to do. Uh, so in the previous lecture, we tried to cover the basic uses of G device tools for long channel MOSFETs, but we were out of time, so we wanted to continue our previous discussion on long channel MOSFETs and also short channel MOSFETs. So before talking about short channel MOSFET, which is our original concern, so first of all, think about physical models. In previous presentation material, we just I just show you the IV characteristics generated from constant mobility model. However, we must include physical models to have physically and even in an engineering sense correct result. So we need to include these two lines in our property line. So maybe you remember that. So in previous case we had properties about band gap narrowing. So can we open, for example, if we come back to our previous lecture material, so then you can find the mandatory default one shown here. If we have a certain device material, then we must specify also this effective intrinsic density, so which simply determine the band gap narrowing effect. Band gap narrowing is quite an important one, but even when we don't use that band gap narrowing effect, we must specify that we will not consider any kind of a band gap narrowing. So in our input file, this property starting from this model equal to effective intrinsic density is mandatory one. However, all other property lines are just optional in principle. So if you don't specify anything, then the simplistic model in that category will be used. In many cases, we don't use anything. For example, if we do not specify any mobility model, then naturally we just use constant mobility model. Then how can you have a constant mobility model? Just to do not anything. Then after that, this program just to try to catch the parameters shown in your DB path, and when you open the DB path, then for your materials you have material parameters. If you change that number, then actually your mobility can be adjusted. However, in your case, please do not change your DB path, because I guess that all of you are using the shared version of this DB path. It means that all of us are using the same material parameter. If you just change your parameters, then you can improve your device performance quite easily, but this is not physically available. So please do not change your DB path file. I think that you don't have any right privilege to modify that file. So anyway, so if you don't specify mobility, then the constant model is used. However, if you specify something here, then that is additionally applied. So additionally here means that this is the name of a certain model's author. Maybe he was a student of Stanford, and so it is related with inversion layer mobility. So If we just say constant mobility model, then usually what we do is people just to measure our silicon material at given temperature and low impurity density. So if we have a low impurity density, then there is no effect from impurity scattering, and usually in this case so-called phonon scattering mechanism determines the mobility. So when we say constant mobility model, it's more or less like we are using just a phonon limited bulk mobility. But this mobility is not for our inversion layer. Electrons inside the inversion layer suffer from additional scattering mechanisms, so it is known that its mobility value is somewhat lower than that of quite lucky case, almost no impurity and quite pure material. And yes, this is a bulk, so this is best case, and this is a more critical case. So when you specify this model, then there are really many effects related with this inversion layer mobility model is automatically included, and it has a long list of parameters, but we are just taking parameters from the author's original paper. So that's the reason why once we adopt this one, well, it is not certain that actually your typical or your fabricated device exactly follow this level of mobility. Mobility can show quite much difference, fluctuation, device to device or process and process. So there is no guarantee that 100% of matching of our mobility value. But at least what we can say is when you add this model, the level orders of your mobility will be much closer to the realistic one. Even in that case, you can have a factor of 2 or 3 differences in your actual mobility. And another effect shown here is this is another name of the first author. This is Canali, maybe Professor Canali. I'm not quite sure. I never met him. And measured this case, so velocity, electron and hole velocity as a function of electric field, but this electric field is lateral electric field, means that the electric field applied to the direction of electronic motion. So if we have an electron, let's assume that this electron is moving in this way. Right now, our lateral electric field is the electric field heading in this direction. Please don't bother with this negative or positive sign. So in this case, this is lateral electric field, and there is another direction of electric field. This is vertical electric field. Inversion layer mobility model shown here usually take into account this vertical electric field. This one determines the inversion layer mobility, and this one, lateral one, determines high field mobility. When you apply quite high voltage to your drain, then in a lateral direction we have a quite high also lateral electric field that degrades the velocity of actually that high electric field saturate the electron velocity. So simply speaking, we have this kind of behavior. When we have relatively low electric field, then we have a well-known expression like velocity proportional to the electric field, and that proportional coefficient called as mobility. This is valid for this relatively low electric field region. And if we go to a certain limit of this model, then beyond a certain electric field, then even though we are applying even higher electric field, it does not increase its velocity. It's like this. You are driving a car. When you drive a car, then let's assume that you are now pushing your accelerator. So in a low velocity region, then when you push it harder, then your speed, car speed will increase. That is quite natural. However, let's think about the extreme situation. Now you are on the highway and you are now intentionally speeding. Then you are pushing the accelerator pedal as much as possible, so as hard as possible. However, it does not mean that your car can move at speed of light. So it will have a certain maximum speed it can have. Quite similarly, in an electric field, we are pushing our electron by applying electric field. So it is accelerated, so its observed velocity or speed increased. However, it has its own maximum speed. So when we apply too high accelerating force, but that does not increase the final speed of our electrons. So simply speaking, this effect is shown in or considered in this Canali model. So you must include these two ones. And please note that this model is suitable for inversion layer case. So if you are talking about different models, not inversion parameters. For example, if you are simulating bipolar junction transistor or PN junction, where the surface mobility is not that important, then the necessity to use this inversion layer mobility is somewhat reduced. This model itself actually contains not only inversion layer mobility effect, also it contains some bulk-like effect also. So people call it as just all in one model. When you just use this model, except for this velocity saturation effect, actually many physical mechanisms related to the electron mobility and hole mobility are included. However, main concern or main point was inversion layer mobility. So if you are talking about different materials or different devices, then maybe you can omit this one. And another one, here you have a different line. So this is related with recombination. Recombination is really important to determine the lifetime of your device. Also, it is very important for the calculation of a leakage current. Leakage current means that, so now you have a certain, for example, planar device, and say that this is your source terminal, which is grounded, and here you have a drain, which is biased to VDD, and here we have a substrate which is once again grounded. This is N plus, and this is a P-type substrate. So when we think about this junction between N plus and P, so P part is biased to 0, and N part is biased to VDD. So if we just consider anode voltage minus cathode voltage, then it becomes just minus VDD. So it is highly reverse biased. So if that is really reverse biased, what we can say is PN junction when reverse biased, it just rectifying the current. It does not conduct any kind of meaningful current. That is our understanding. However, if we have very bad situation of tons of SRH recombination center nearby this junction part, then it can be a source of leakage current. It can generate so electron hole pair at this depleted part, and this electrons is moving to the n-type region, and this generated hole is moving toward positive p-type region. So we can have a lot of unexpected or unwanted leakage current. So simply speaking, it means that now electrons are moving in this way, so negative charges are escaping from the device. It means that positive charge is incoming into the device. This is taken as a positive sign, positive convention for terminal current. So in this case, what we can say is our drain current shows somewhat high positive value here. Now we have, simply speaking, you apply high voltage, so you expect positive current. Yes, it's true. However, since gate is turned off, so the current between source and drain should be minimized. Even when we minimize this leakage current, even in that case, if our junction between N plus and P substrate is not perfect, then there can be another potential contributor to the leakage current. So in this case, if we wanted to think about this leakage current, we need to include this SRH. S Shockley, R read, H hole. So that's just the combination of three researchers of a research paper. So then maybe you can ask me this question: is it really important? But why we don't care about this important one up to now? When we talk about the current conduction mechanism through source to drain path shown here, actually this SRH is not that important, because this current conduction is just due to the difference between quasi-Fermi potential in this source region and drain region. If we apply high drain bias, then it conduct. There is no contribution from SRH. However, as we have discussed up to now, if we have another contribution shown here, or also we can have another contribution shown here, then this is more or less related with SRH center, because this one becomes the main mechanism to supply electron hole pair. Once we have electron hole pair, then they can move. In the case of our usual current conduction, here usually we have so many electrons. This is reservoir of electrons, so we have more or less sufficient capability to supply electrons. Only the limiting mechanism was the energetic barrier between this source and channel region. So that is the way of changing the current through channel region. However, in this case, a more important one is the supply of our electron hole pair. Once electron hole pairs are generated, then their movement is quite straightforward and there is no force against it. So in this case, generation really determines the current. So they have two different situations. So now let's come back to our practical case. So maybe you can ask me this question. Up to now, we have thought about IV characteristics and without this SRH recombination center. So therefore, maybe it is not that important. But in practice, it is really important. Why it is important? If you are talking about logic device, then in many cases your devices are turned off. When you turn off your device in your system, usually what you do is two cases. Gate is turned on, however drain is turned off. In this case, yes, since drain to source voltage equal to 0, so that is really 0 current. However, think about the opposite case. Now your gate is turned off. However, you are driving your drain with high voltage or low voltage depending on polarity of your device. In this case, if our gate is perfect, then we can suppress the current through channelism. However, as we have shown here, the gated channel is not the only way to have current conduction. We have another one through this source and substrate path. So in this case, we have a leakage. So when we have a logic gate, usually we have a PMOS part here and NMOS part. So usually this NMOS part is used to pull down our voltage down to ground, and this PMOS part is used to pull up our voltage to the VDD level. So usually this part is called as a pull down circuit, and this one is a pull up circuit. So they are competing, and if one of them wins, then it determines our output voltage. If MOSFET part pull down wins, then our output voltage will be 0, and if other ones, the PMOSFET part is wins, then our output will be VDD. So simply speaking, when you consider your logic system, logic devices, always your devices, except for very short period where really the current is flowing, and when we charging and discharging the output capacitance, except for that short period, in many cases our transistors are turned off, and in this turned off case, the major concern is really the leakage current. So this is primary concern of our technology, and who decide this leakage current. Our best aim, our best hope is, okay, this leakage current is solely determined by this gate, and in many cases, if we are successfully fabricating our devices or developing our devices, then it's the case. Leakage current is fully controlled by only gate voltage. But if we are unlucky, or if we are not able to make successful devices, then even though we turned off our device with low gate to source voltage, but still we have a leakage current. So simply speaking, in practice, if you are entering into any kind of or joining any kind of serious semiconductor company as a device engineer, actually what you have to care is not only this on current, but this leakage current, or sometimes called as off current. this is a more important one because the lifetime of your electronic system means that battery life is determined by not by on current but by this off current. You just leave your cell phone, and after several hours later, you come back, but a certain implementation just to survive from several hours long duration, and some just fully discharges and cannot be used any longer. So that is determined by this leakage current, or as a special bias condition we call it as off current. So inclusion of these parameters or these physical mechanisms are very important to have reasonable data. Also, I strongly recommend you to, when you perform your term project, please include these effects in your, of course, project. Otherwise, you can highly overestimate your performance. Then you may be quite happy because you have a high performance device, but it's not that realistic. Okay. Well, anyway, here now you can see quite interesting result. Here you have, I'm not quite sure this is red or brown. It seems like a brown curve. And these brown curves are obtained from the same structure, however, without any kind of physical mechanisms. So this is with VDD, VDS equal to VDD, and this is a relatively low bias condition. So we must compare these two. Yes, this curve and this curve. Once again, this brown one is without mobility model, and this blue one shows the result with mobility model. So can you recognize the difference? If we include this model, its value at gate voltage equal to 1.2 VDD. It's like something like some numbers around here. And when we have correct mobility model, then we have the numbers around here. It is like just 10 times reduction of our current. Why? It is simply because without this physical model, mobility model, the default value of our silicon mobility is around 1,400 square centimeter per volt second. If we have quite a pure silicon material at 300 Kelvin, this is the value we can expect. However, it is never achievable in practice because in our case we have doped quite a lot, and also our electron channel is quite close to the very how can I say, rough surface between silicon and silicon dioxide, so we cannot expect such a high mobility value. So in reality, if we have the values like 200, I will be very happy with this number. In many cases, electron mobility can be about 100 or sometimes even lower can be achieved, and we are currently living with that number. Mobility value is not orders of 1,000, but it should be regarded as low numbers, low multiple of 100 or even lower. That is the one thing we have to be very careful. So simply speaking, without this mobility model, you can actually 10 times higher mobility or drain current value, so you can reduce your, for example, delay time quite a lot, but it never happens. So that's the reason why actually in practice improving mobility is so important. Actually, this is one of the most important one to have a high performance device. And nowadays, the way to maintain this high mobility is closely related with stress engineering, or it is also related with portion of germanium in our germanium silicon germanium alloy. So yes, so stress is so important. Anyway, now you can understand we need to include a reasonable model. And also when we have this semi-logarithmic curve, yes, previously we had this line. There is almost no dibble because we have a quite a long channel device, and even with this new physical model, it is still true that there is no dibble because dibble is a function of a channel length, and since we have quite a long channel, so it is quite easy to understand. But point is, between these two lines we can have a certain amount of difference. It is almost one order of magnitude. So inclusion of a realistic mobility model can reduce our current significantly. And yes, so in many cases it is just reducing this value significantly. Okay. Now, up to now we have thought about how can we calculate ID as a function of gate source voltage and under a fixed condition of VDS. Drain voltage is fixed. After that we just sweep gate voltage, and now we have this kind of curve. So this curve gives us once again very important quantities. Yes, this is op current, and this is corresponding to on current, and their difference is measured as dibble, and also their slope. Here we have a sub-threshold slope, and it should be around 60 millivolt per decade if we are talking about gate all around transistor. Of course, when you measure this curve, or when you measure sub-threshold slope from this curve, you will find that that is somewhat lower than 60 millivolt per decade. Somewhat worse means that about 100 or something like that. However, this is only due to it is obtained from planar devices. Okay. Now let's go to the output characteristics. Instead of this ID versus VGS, now we have ID versus VDS at given gate voltage. So that is usually called as output characteristics because this drain terminal is regarded as an output terminal. So we have this kind of description. Now, depending on gate voltage, their behavior looks quite different. So we must consider different several gate voltages. If your applied gate voltage is lower than threshold voltage, then it is certain that when you draw your ID as a function of VDS, then you will have just a horizontal line. Although you change it, your drain voltage, but it does not conduct at all. That will be the case for gate voltage lower than threshold voltage. But once you apply higher gate bias voltage, higher than threshold voltage, then you will have a well-known this output behavior that can be simulated by this kind of solver routine. And Now, even in this case, without physical models, now you will have this number. Yes, for example, here we have a VGS is 0.6 volt, and if we reduce it further, then we will have just a horizontal line which cannot be distinguished. However, after that, when we increase our gate voltage about 0.2 volt, then now we have a saturation current is increasing quite rapidly. I mean that this difference and this difference, are they equal, or which one is larger? Of course, this one is larger. It means that saturation current follows the parabolic rule of our long channel description. So maybe you can remember saturation current follows the square root of gate overdrive voltage. That's the reason why we have this kind of unequal difference. But this is only obtained when we have this long channel behavior. Of course, when you go to short channel, we have a different saturation behavior. We'll see later. And when we include inversion layer mobility model, then these lead curves are obtained from physical models. Then what we must compare is this guy and this guy. Huge reduction. And when we have 0.8, where can you find 0.8? Now we have 0.8. So in reality, the impact of a mobility model is so severe, so you cannot neglect it in any means. So you will have quite a lower drain current, and you can see that still its general shape itself looks similar, just it is squeezed toward downward. Okay, and another one is here we have included velocity saturation effect with specification of a canali that introduced this one. Previous model, this one just obtained without canali, just in our G device specification, we just included this one, and additionally we have added, so this canali model. Then what happened is, yes, this one is inversion layer mobility model only, and this one shows the combined result of inversion layer mobility and velocity saturation. It shows some differences, but it's not that drastic. Why? Only because this device is long channel device. In the case of a long channel device, actually this velocity saturation effect is not that important, but we will see that this is not the case for short channel device. Okay, now you can draw also electron density. For example, here we have x equal to 0 position. This is set as the interface between silicon and silicon dioxide, and you can draw just interface carrier density. What does it mean is here we have a source contact. Actually, source contact is located here, and this part is a source region, and also drain contact is located here, and here we have drain region. Please note that this is not that short actually, because we have quite a long channel, so relatively it looks like short regions. However, it is still already 50 nanometer, and this is 50 nanometer, sufficiently long. And now you can see that the gate bias is VGS equal to VDD. So we have gathered a lot of electrons already in this source region. Here we have a source region, and electron density is orders of 1, 2, 3, about 3 times. The value is 3 times 10 to the 19 per cubic centimeter surface density. I think that this is not that high actually. In many cases we have even higher value, but in this specific example, our maximum electron density in channel region is around 3 times 10 to the 19 per cubic centimeter. And if we apply just VD equal to 0 volt, if that happens, then maybe that would be our electron profile. So channel is uniform, and electron density is just determined by this gate voltage. However, if we apply higher and higher drain voltage, then now near the drain end, now its electron profile goes down. Now we have a relatively small number of electrons that is observed here. However, we have to have current continuity. It means that the current calculated at this point and current at this point should be the same. How can we have that happens? For example, here we have 3 times 19 per cubic centimeter, and in its minimum level here, we have more or less 3 times 10 to the 16 per cubic centimeter. We have 1,000 times smaller electrons occupying this position. Then how can you match this huge difference? Of course, this guy, electrons at this point moves much faster than electrons in here. So although we have the same current, there are many electrons are slowly moving, and here we have a few electrons are quite fast. So that's the way we match the current continuity. And another one we have to be a little bit careful is this one just shows the interface electron density. In this specific case of on current condition, usually it is known that electrons, especially in this case, is not concentrated on this surface layer, but it is widely spread over this along the vertical direction. So it does not, this 1,000 times difference does not show that the total electron density at this position, at that position, are really 1,000 times. So we must a little bit careful. But that two-dimensional effect will not be considered in the lecture. So if you are interested, I strongly recommend you to do this job. You have a two-dimensional electron profile, then please try to make a cut not along this y direction, channel direction, but make a cut along x direction. At a certain point, for example, this one, 0.1, and at another point, like for example, 1 micrometer, then you will find that there is a somewhat different distribution of vertical distribution of our electrons. So simply speaking, if we have quite a good control over our electron charge by gate, then since it has strong controllability, so now electrons are just attached to this interface. Only due to this silicon dioxide, it cannot go into this gate, but this is quite attractive. So it is really just attached to this interface. However, at this point, it is no longer the case. So gate is not as attractive as in this point. So electrons are just spreading. So we are just observing that point. So if we measure the electron density simply at the interface as we do right now, then we will see that, oh, there is almost no electron. Yes, there is not many electrons, but where can you find electrons? If we go to deep into this, not very deep, but not exactly interface, if we go to a little bit deeper into our devices, then you will find a meaningful number of electrons. Okay. Anyway, now let's go to homework 18. So homework 18 is only related with long channel MOSFET. From now on, we'll talk about short channel MOSFET, but I'll just left it for your further homework, later homework exercise, because there are a lot of things you have to do right now, even with this long channel MOSFET. So please have your time. So I already asked you to prepare this homework 18. So I hope that you have already done something. So due is quite tight. So Wednesday morning, you have just 2 days to finish all of exercises, but I hope that you have already done most of them. So please, if you have not done it sufficiently, then please do it right now. So because your term project will be related with this kind of exercise, you should be able to use this program to use your generated structure. So otherwise, your term project will be just a description of a certain structure. That is not our final goal. Our final goal is to optimize a certain device option. So for that purpose, we should be able to generate a structure and predict the performance of that structure and change it again. That is required. So please spend a sufficient amount of time to perform this, the basic long channel one. Our main topic is this short channel MOSFET one, because actually the one you have to simulate is really short channel. Will you simulate long channel in your term project? No, actually. Nowadays it is almost difficult to see long channel devices, because think about this one. You wanted to make a long channel FinFET. If you really wanted to do that, then you have to make your dummy gate longer than the others. But how did you make your dummy gates? You made uniformly spaced polysilicon or amorphous silicon. Uniform lines were drawn. However, if you wanted to make a long channel device, then you must intentionally draw very long dummy gates, and every process margin will be changed when you change your channel length. So therefore, it is difficult to find out long channel applications in most advanced logics. So everything you are simulating is actually long channel devices. So here you can see these numbers are exactly same as before. We are sharing the same technology. The change is from 1 micrometer. Now we have a much shorter 50 nanometer. Why it is 50 nanometers short? We are now using 10 something nanometer, and we don't think that is 50 nanometer is short. But long, concept of long or short, it is really related with technology. In this technology, 50 can be regarded as short. In our FinFET case, 50, if we make a 50 nanometer long FinFET, then certainly it will be much long channel device. So it really depends on actually which one determines the short or long. Actually, this vertical structure determines short and long. If that vertical structure is scaled, then also lateral length is also scaled. If you allow even shorter device, then what you have to do is also scale down this vertical one. And as I told you in a previous lecture, the 1.2 nanometer, in fact, EOT of this 1.2 nanometer, this is the limiting value of our pure silicon dioxide dielectric. So in our technological history, we have achieved 1.2 nanometer thick EOT. After that, people try to reduce it even below with pure silicon dioxide, and they have found that actually gate current is explosive. So that's the reason why they stop using this pure silicon dioxide. After that, for a while introduces stress. After that, introduce high K metal gate stack in it. Okay, so now please make once again. So actually you can do it by yourself, but anyway, please be careful. I think that I think that I have a long file. For example, here I have a long.cgns. I prepare my PPT with screenshot, and I did not change my screenshot, so I will upload the short channel one after this session is over. But anyway, you can also try it by yourself. Okay, so now when you have your short and long channel devices, if they are drawn in the same scale, you will have these two different shapes. Lower one, bottom one is long, and upper one is short. So you can see that the scale is quite different. And now let's try to see the input characteristics. Please reuse your input file. I think that when you correctly change your input file or structure file, then actually you can reuse just the biasing conditions without any modification. So you will have this graph. So here you have a long channel device, the previous one. So also physical models are included. And when you have a short channel device, you have a somewhat higher drain current. So why it is? Because here we have this relation. Drain current is inverse proportional to the channel length, and we have 50 times differences, 20 times differences in our channel length. So current is highly increased in this case. So it is beauty of our microelectronics. We have used smaller area, and we have obtained even better performance. That is, I think that this is quite a rare case in engineering. In many cases, if you wanted to have a higher performance of something, if you wanted to make something which shows better property, usually you have to spend more resources, in many cases spaces. So if you make a quite a comfortable house, you need wider land, and if you make a luxury car, then your car should be larger than usual. However, in this microelectronics, so this is a little bit different. If you can make it smaller, then not only saving your money, even a car, building a car, then if you make a smaller car, then you can save your cost. That is quite much understandable. However, in this case, even performance looks better. Oh, okay. So now we have covered this issue in our previous semester, in the last semester, but I wanted to repeat it once again. So we have a reduction of a threshold voltage even at a low VDS. If you are familiar with the short channel effect, then maybe you know that there is an important effect of dibble. However, please note that dibble is the effect dependent on drain voltage. If we apply higher drain voltage, then threshold voltage is lowered. That is dibble. However, in this case, even without applying any kind of a meaningfully high drain voltage, still our threshold voltage measured at 50 millivolt case shows somewhat different values. So you can see that 50 millivolt difference is observed in this same technology, but just to make a shorter one, then it shows a different threshold voltage. So it is called as charge sharing effect. So when we just draw the 0 and 0 volt case, gate voltage and drain voltages are biased to 0, then these two curves shows the conduction band profile. So actually this one, the difference between this lower number and higher number is regarded as the barrier height, energetic barrier height to be overcome. So in the case of a long channel MOSFET, the value is given as this one and this one. But if we have a short channel MOSFET, the red color is the barrier profile we have. So then we can ask ourselves, what is the effective barrier height for this case? Actually, we have this value as a maximum barrier height. It means that compared with this long channel MOSFET, this short channel MOSFET is regarded as a somewhat easier potential barrier because there is a slight reduction of maximum peak energy level. So it is relatively easier to turn on this device. So therefore, even without applying high drain voltage, from its starting point, its threshold voltage itself is reduced, and now we have a dibble. In this case, now we additionally applied apply a high bias voltage to our drain terminal. So you know that this one, for short channel device, this curve itself is already shifted from that of a long channel one, but also starting from this number, when we apply higher drain voltage, then threshold voltage is shifted quite a lot. So when we measure this number, usually dibble is expressed as this way. Dibble is you measure threshold voltage twice. which is quite low bias voltage and quite high bias voltage, and that is divided by your high bias voltage minus low bias voltage. So that's the reason why here we have a volt per volt scale. Change of threshold voltage, which is written in volt scale, divided by also change in your drain voltage. That is another volt. So when you write down in this dimension, as I told you before, 100 cannot be acceptable. 45, yes, it's good. And if we go to values higher than 50, 60, then this is quite a danger. So we wanted to keep this value as low as possible. But you know, nowadays everything is just short channel devices, so we cannot make it as a zero. Zero is not our ultimate goal. We wanted to make some engineering trade-off between certain quantities, and these numbers around 45, it looks quite reasonable. So now we have values like this. So I think that if you are performing certain kind of term project, one interesting topic, possibly interesting topic, is changing just channel length of your transistors. Then try to measure dibble. You will find that actually dibble gets worse quite rapidly. This is length and your dibble. Then if we have quite a long channel device, for example 1 micrometer, dibble is almost undetectable, just 0. And if we go to shorter and shorter, then for example in this case, if we are going to 50 nanometer, then we have 45. Then what will happen if we go to 40, 30, 20? Then actually it goes quite rapidly increasing. So maybe you can try to make this kind of exercise using your computer program, then say that which one is the best one. We wanted to minimize our cell. However, channel length cannot be reduced any further. Then if you are the only concern is dibble, then actually the answer is quite simple. We have to use very long channel device. However, that does not give us the engineering solution. We have to minimize. So we must compromise at a certain point. Well, I will just stop 50 millivolt per decade. That is required. Okay, so now when we draw conduction band once again, now this is the additional reason of our previous case, observed dibble. So this red one is actually the one corresponding to this one. The same data points are shown here. Previously it was the data span or axis start from 0 and at 1.1 micrometer, so it looks quite narrow. However, in this case we are just considering only short channel device only. Now it is just expanded only along x directional. So now you can see that this is Vd equal to 0 case. However, when we apply high drain voltage, so this drain just pull down our conduction band profile. So in this case also dibble is quite easily understood, because here and there also we have a reduction of peak energy barrier seen from our source side. So now once again it becomes easier than previous case, drain voltage equal to 0 case. So that's the reason why we have additional reduction of threshold voltage here. So actually, if we, so they are actually charge sharing and dibbles are cross coupled. So we cannot think about the case where charge sharing effect is so severe, but there is no dibble. There is no such device. However, once we have a certain gate length, then the difference between long channel and short channel, that is not that important, because once the circuit engineer understand this device should have a certain given threshold voltage, then they can design their circuit without problem. The only problem is, although that shows a certain threshold voltage at given drain bias, but when it changes, actually dibble is important for circuit designers, because circuit designers can select the length of their device when they design, but they cannot select their bias conditions, because it is given as 0 over VDD, and it is not possible for them to control over this number. So that's the reason why dibble is regarded as important short channel effect, and actually dibble is the, usually we call it as show stopper. What is a show? The show is scaling down. When we doing the scaling show, then this show is stopped by eventually by this dibble. So okay, so now let's go to the next one. So this one shows the result only with inversion layer mobility, no saturation velocity. I mean that Canali model is not used. So in this case, we have a certain curves, but point is, when we include Canali model corresponding to velocity saturation, then now you can see that still we have much different behavior of our transistor. So please make a comparison. Here, once again, this is a short channel device. We have a severe effect of a channel, velocity saturation model, and let's come back to our long channel one. We will see the graph corresponding to previous one. Yes, this was the long channel case. In this case, with or without velocity saturation effect doesn't make big difference. Of course, the current is reduced, but that was not that severe. But now we are observing that without this velocity saturation effect, once again we can highly overestimate the on current of our transistor. So that should not happen in reality. You should also consider this Canali model. Okay, so please add or consider correct physical models. Okay, today's lecture, I have already finished today's lecture contents. So although I have shown it to you just with my result, but if you, when you try to do it by yourself, you will find that it takes time. First of all, the simulation itself takes time, one point. And another one is, once you have the output file, the output file itself does not give you some internal quantities For example, if you wanted to draw this line, then from your device structure file, you have to collect some important quantities. So that's the reason why you have to make an exercise. Which one is important quantities? If you open your CGNS file, there are a lot of variables available, and which one is important? If you are simulating MOSFET and if you are digging some hole related quantities, that is just a waste of time. So you have to understand which one is important quantity and which one is irrelevant quantity. That is the result of your exercise. Please spend, once again, sufficient amount of time to do this one. So I'm afraid that actually you'll be just overwhelmed by this huge amount of work related with this one. But this is as much as we are working with this device engineering, this is our job. Means that we have a clear goal, and in order to achieve that goal, we have to make repeated experiments or calculation or any kind of idealization. Many different jobs to be done to achieve the goal. Well, I think that that's it. So, do you have any question on today's lecture contents? If not, let me just wrap up today's lecture. Thank you.